freezing point depression and boiling point increase. All right, the equation for calculating freezing point depression and boiling point increase is roughly the same. Okay, and you start out the change in temperature. Okay, a delta triangle is delta, Greek letter delta. The change in temperature. This temperature is the freezing temperature. The change in freezing temperature. So we're not looking. This variable is not the actual freezing temperature or the actual boiling temperature. It's the change that occurs. So you first have to know what the temperature of freezing or the temperature of boiling of the pure solvent is. Okay? But the change in that temperature of freezing or boiling is equal to, this is called the Van't Hoff factor. Van't Hoff factor times a constant for that particular solvent. A constant for that solvent times M, which is called the molality.
Is that an I?
That's a, yeah, I use a sort of a script I.
And what's that called?
It's called the Van't Hoff factor.
No, Van't Hoff, is that two different words?
Yeah, it in whatever language this is, it's the same parent name or last name. Okay, like de Guzman. Okay, it's like Van't Hoff.
Yeah, they sound like.
Okay. All right, so this then is a constant. This is a constant specific to the solvent. So only this solvent, only the chemical that's doing the dissolving, has this constant. Okay? Every other solvent has a different constant. Okay? And this is a concentration in a concentration unit called molality. A concentration unit called molality. So you need to this equation is a really important equation. You have to memorize it. I mean, it may be in your unit handout, but this is one you need to know. Okay?
Is it in our references?
I don't know. All right. Now let's talk about what M is first. We can talk about all of these in a minute. First, I want to talk about what M is. Okay. M is a measurement of concentration, and you have to usually calculate it. Okay, it can be calculated, and the concentration called molality, which we use the small letter M for, is a ratio of the moles of the solute, the thing being dissolved, the solute, moles of solute over the kilograms of solvent. Moles of solute over kilograms of solvent.
Why is the solvent measured in kilograms? Or is that
As opposed to grams? Or what?
solvents are generally liquids, aren't they?
For most of the stuff we do in chemistry, yes, but no, they're not always. The air is mostly nitrogen. And also all the other gases in the air are dissolved in that nitrogen by definition. We said that when you can't tell which one's the solvent, because one isn't really doing the dissolving. The one in the greatest concentration is the solvents. And so you measure it in the amount of solvent because of the kind of behavior that best fits this. We're trying to figure out the change in temperature of the freezing or boiling point. Okay, but kilograms, I'm not sure why kilograms were. I know the reason that kilograms as opposed to grams was chosen, so the numbers would be more manageable. Most of the numbers will come out to be, not really, really small numbers and not really, really big numbers. So that's why that was chosen. Okay, and the reason we do moles per moles over some mass unit has to do with the kind of behavior that best reflects this equation. Okay, it gives us kind of a straight line result. Makes it easier for us to predict what's going on. Okay, all right. Now the Van't Hoff factor is it can mean in high school chemistry we limit the Van't Hoff factor to a very simple concept. The Van't Hoff factor is the number of particles the solute breaks up into when it's dissolved. The number of particles the solute breaks up into when it's dissolved.
That's what M stands for?
That's what I stands for. M stands for this, molality. M is concentration. I is the number of particles that each formula unit of that solute it breaks up into. Alright, so I then, for NaCl, if I've got solid sodium chloride, table salt, and I put it in water, I get Na plus, because that's the sodium ion, and I get a chloride ion, and so I equals 2. Does that make sense? Well, how many particles did I break up this formula unit into? 1, 2. Okay. Calcium chloride, on the other hand, when I dissolve it in water, I get 1 calcium ion, and I get 2 chloride ions. So what is I for this solute? 1, 2, 3. Does that make sense? All right, how about this? Scandium sulfate. 2 of these and 3 of these. Put these in water. Should put a solid there, symbol. Okay.
Scandium sulfate or whatever is called the solute and the water is solvent.
Water's the solvent, yeah. I'm going to have 2 scandium ions and 3 sulfate ions. So what is I in this case? Okay, 5. Good. All right.
So you count it, you know,
You count the number of particles each formula unit breaks up into. Okay? Now, not everything that dissolves in water has an I. This only applies to those things we could write ionic equations for. So going back to ionic equations, Unit 5, I think it was, we had to learn to write complete net ionic equations. This is the same process, basically. We're breaking up the formula unit into individual particles. Well, which formulas can break up into particles? Which formulas break up into particles? There were only 2 kinds of chemicals that broke up in 2 classifications of chemicals that broke up into particles. Anybody remember what they were? Not ionic and polar, no. But ionic is true. I wouldn't start it with an S.
You said what? You said what?
What kind of chemicals break up into separate particles like this?
Do you count polyatomics different from ionic?
No, polyatomic, something that has a polyatomic ion in it is ionic. You can tell if it's an ionic compound, usually because it's a metal bonded with a nonmetal, or if it contains a polyatomic ion. Okay, so the two kinds of chemicals that break up into particles will be ionic or acidic. Okay, so,
I remember that.
okay, now this is not ionic and it's not acidic. This is table sugar. This is like sugar. Well, it's not table sugar. It's a simple sugar. Okay, like glucose, yes. But it will dissolve in water. But when it dissolves in water, it doesn't break up because it's not ionic and it's not acidic. Okay? But it just becomes aqueous. Alright, so what is I in this case?
1 to 1.
Yeah. There you go. Alright? So that's the Van Hoff factor. There's molality. And I guess Thursday then we'll start looking how we use this equation then to make calculations. What? What now? That Hannah?